Today we're going to be discussing section 4.4 about theorems about zeros of polynomial functions. So we're going to find a polynomial with specified zeros. For a polynomial function with integer coefficients, we're going to find the rational zeros and other zeros if possible. And then we're also going to learn Descartes' rule for signs of polynomials and determining the number of real zeros that we get with that polynomial. So starting off with a quick example, here we're looking for a polynomial of degree 3 with these numbers as zeros, 4, 3, and 6. Let's simplify the function, and we're going to assume that the leading coefficient is 1. So if we have zeros, x equals -4, x equals 3, and x equals 6, we must have had the factors x plus 4, x minus 3, and x minus 6, because those are the three factors that would produce those zeros. So then our function f of x must be the product of those three, x plus 4, x minus 3, and x minus 6. And now to simplify the function, which is what Pearson expects, we actually need to multiply out this function. So what we're going to do is multiply out the last two terms. We're going to leave that first term here for now. Now let's FOIL out these two terms. We get x squared minus 3x minus 6x plus 18. That gives us x plus 4, x squared minus 9x plus 18. So now we need to multiply out a binomial with a trinomial, which is not something we've seen yet. But all we're going to do is take our, take our first term, x, and distribute it to all three terms here. Then we're going to take our second term, 4, and distribute it to all three terms as well. Then we're going to combine any like terms that we find. Let's do that in the next column. We have x times x squared, which is x cubed. Then we do x times a minus 9x, which is minus 9x squared. And then we do x times 18 plus 18x. Now we're going to distribute the 4, so we have a plus 4x squared. Now 4 times a minus 9x, minus 36x. Now 4 times 18. Which I believe would be 72. All right, so now we just need to combine our like terms. We have our x cubed term. Then we have a minus 9x squared and a plus 4x squared. That's a minus 5x squared. Now I have a plus 18x and a minus 36x. That's minus 18x. And now I have a plus 72. And so that is the final simplified answer. It does have leading coefficient 1. I could plug in all three of those zeros and double check, but they will give me 0. And that is the function I was looking for. So now let's look at some irrational zeros. So assuming that b is not a perfect square, and the square root of b would not simplify, irrational zeros are of the form a plus some c times the square root of b, and a minus c times the square root of b. We also have a rule that if a plus c square root b is a 0 of our polynomial, then its conjugate, where the sign is actually flipped, a minus c root b, is also a 0. So for example, if I have -3 plus 5 root 2 as a 0 of my polynomial, then its conjugate, -3 minus 5 root 2, is also a 0. So when you see one of them appear and you're asked to find another 0, it's very likely the conjugate. So you should check flipping the sign on the square root part and see if that's also a 0. This rule says it will be. So let's see an example of that. Suppose that a polynomial function of degree 3 with rational coefficients has zeros square root 3 and 4. Find the corresponding 0, or the missing 0, and the polynomial function, assume that the leading coefficient, again, is 1. So based off that theorem that we just saw, if the square root of 3 is a 0, then negative square root 3 is also a 0. We always got to flip the sign on the square root part. There's no whole part with the square root of 3. There's no 2 plus root 3. It's just root 3 alone, and so the sign flips to negative root 3. That's its conjugate, which is our other 0. And then, of course, 4 is a 0. That was given. So then our factors are x minus 4, x minus root 3, and x plus root 3. That is also a polynomial of degree 3, and it has leading coefficient 1, so that is our function that we are looking for. But now let's multiply this function out. If I leave the x minus 4 term in the front for now, then I'm going to multiply my x minus root 3 and x plus root 3. My first terms give me x squared. My outer terms give me x root 3. My inner terms give me minus x root 3. And my last terms give me a minus 3. And so now if I want to simplify this, notice my middle two terms cancel, which is really convenient. I get x minus 4 and x squared minus 3. And that's really easy to multiply out. I'm going to FOIL again, though, so I get x cubed minus 3x minus 4x squared plus 12. And because I did outer then inner, this isn't quite in the right order. And so let's do that here. X cubed minus 4x squared minus 3x plus 12. That is the polynomial we were looking for, and root 3 was the missing 0 that we were looking for. And so that is it for this type of problem. Okay, so now for this problem type, we're given the polynomial and we're given a 0, and we're asked to find the other zeros. So we know then, with this polynomial, that x plus 6 is a factor of f of x, right? Because we're given this minus 6 over here, we know x plus 6 is a factor of f of x. Well, if we wanted to see what the quotient was, it'd be really nice to do our long division. But instead of doing long division here, I want to practice using our synthetic division so we can continue to get quicker at that. So using synthetic division, let's see what happens. With that, I write my negative 6 in my little hat, and then I write down the coefficients of my polynomial. 1, 5, negative 8, negative 12. Give myself space for a row, and then I draw a bar. Step 1 is always to drop the 1, and then we're going to bring it up by multiplying the 1 with the thing inside the hat, the negative 6. Now we always add the 5 and the negative 6 to make negative 1. Now that negative 1 multiplies with the negative 6 again to be brought up, which gives us a positive 6. The negative 8 and the positive 6 are added together, and we get a 2. We get a negative 2. Now we do negative 6 times negative 2, and we get 12. When we add negative 12 and 12, we get 0. That 0 is great because that's our remainder. That tells us x plus 6 definitely is a factor of f of x. And it tells us f of x equals x plus 6 times x squared minus x minus 2. So we can pick up the coefficients again from what we got down here. X squared minus 1x minus 2. Well, that's something that we actually know how to factor, because if we look at x squared minus x minus 2, when we factor it, we think about things that multiply to negative 2 and add to negative 1. We fill in our x's. Well, that clearly is going to be 2 and 1. And I want the minus to win over all. And of course, they're alternating signs. So now I know f of x overall, pulling in the x plus 6, and then the factored quadratic, I have f of x equals x plus 6 times x minus 2 times x plus 1, fully factored. So now we have all of our zeros, of course. X equals negative 6, x equals 2, and x equals negative 1, as the problem requested. Now let's look at the rational zeros theorem. Here we're going to assume we have our standard form on our polynomial, where we have the exponents in decreasing order all the way down to our constant term. Let's suppose that all of the coefficients are also whole numbers. So we are going to consider a rational number denoted by p divided by q that is fully simplified. Okay, assume p over q is fully simplified. You can't reduce it anymore. Then if p over q is a 0 of p of x, then we actually get that p is a factor of a0 and q is a factor of a sub n. So that is that a0 is p times some number, and an is actually q times some number. So let's see how we would use something like this. Again, we're going to think p, a0 is p times some number, an is q times some number, and we're looking at p over q being a 0. Well then, let's look at what a sub n here is. A sub n is 3, and a sub 0 is negative 4. Basically picking up the first term and the last term. Okay, well starting with a sub 0, or my p-value, p can be all things that divide negative 4. P is, let's write that down, all numbers that divide negative 4. So that's plus or minus 1, plus or minus 2, and plus or minus 4. Q is all numbers that divide 3, our a sub n. Well, that's plus or minus 1 and plus or minus 3. That means all of our p over q options are, so taking plus or minus 1, basically I'm going to set the bottom q, pick a number, and then apply it to each of the top ones. So if I assume q is 1, then I get 1, 2, 4, or I get negative 1, negative 2, negative 4. That applies to plus or minus 1 across all the different plus or minus 1, 2, and 4. Now looking at using the 3, I can get 1 over 3, 2 over 3, and 4 over 3, and the negatives of those. Negative 1 over 3, negative 2 over 3, and negative 4 over 3. And I know that still seems like a long list. That would be a lot of numbers to try in our polynomial. But the cool thing is, if you think about it, we went from an infinite amount of numbers across the entire number line to just some set of around 10 numbers to try. So it does help us reduce it a lot using this principle. Still a lot to go with, but again, just kind of brings it down to a more manageable level. This is now finite. At least I could do this in a finite amount of time and find all my possible rational zeros of my function. So let's actually use it in practice. Let's find all the rational zeros and then the other zeros of this polynomial. And I am going to take the time to go through the list in a strategic way. Sometimes you have to go through 3 or 4 numbers until you find all of your zeros. So let's go through that process now. So given that f of x equals x cubed plus 5x squared minus 7x minus 35, find all the rational zeros. So starting with our options for p, p must divide our constant term, which here is negative 35. So I can have plus or minus 1, plus or minus 5, plus or minus 7, and plus or minus 35. And then for q, my a sub n here is just 1, so I just have plus or minus 1. And so I actually don't have to worry about q here. Let's just strategically go through the options for p. And let's start with 1. And we're going to do our synthetic division on each of these different zeros, see which one has remainder 0, and then we'll be able to find all of our rational numbers. So starting with 1, we got to look at our coefficients. 1, 5, negative 7, negative 35. And so I give myself some space and I draw a line. And we drop the 1. And then I do 1 times 1. Bring it up here. I get 1. 5 plus 1 is 6. 6 times 1 is 6. Negative 7 plus 6 is negative 1. Negative 1 times 1 is negative 1. Negative 35 minus 1 is negative 36. Oh, so that one is not a 0. That one was not useful. That's okay. Let's try negative 1 next. Okay, we're looking at 1, 5, negative 7, negative 35. So now I give myself some space. I draw a bar. I drop the 1 first. I do 1 times negative 1 to bring it up here. I do 5 plus negative 1 to give me 4. 4 times negative 1 is negative 4. And then I do negative 7 plus negative 4, which is negative 11. Negative 11 times negative 1 is 11. And 11 and 35 gives me a minus 24. So that is also not a linear factor. Well, let's keep going. Let's try 5. 1, 5, negative 7, negative 35. Give us some space, draw a line. All right, drop the 1. 1 times 5 is 5. 5 plus 5 is 10. 5 times 10 is 50. Negative 7 plus 50 is 43. Bring it up here, I get a 43. And 35 of 40, negative 35 of 43 is positive 8. We still haven't found it. I'm going through this process with you to show kind of what you also should expect for your homework, of sometimes you have to go through it a few times to find the right value. But it's okay, it's a finite number, let's keep going. If I pull out a negative 5, I am then looking at 1, 5, negative 7, negative 35. Give myself some space. And now I drop the 1. 1 times negative 5 is negative 5. 5 and negative 5 is 0. 0 times negative 5 is 0. Negative 7 plus 0 is negative 7. Negative 7 and negative 5 is 35. Negative 35 and 35 gives us 0. Yay, we got a 0 for our remainder. So this is great. This is a yes. And for note-taking purposes, these were both no's, right? We did not get a 0 in that last spot until we got to negative 5. That tells me f of x equals x plus 5 times x squared plus 7. Oops, x squared minus 7. I pick up the coefficients down here. So x squared plus 0x minus 7. So all of that work just to get to this point. Now I'm going to move to another slide just so that I can have a little more room. We just found f of x equals x plus 5, x squared minus 7. After multiple synthetic divisions, we got to this result. Now, x squared minus 7 is something we want to factor with one more step, but it's not too bad to do. Because note, if I take x squared minus 7 and I set it equal to 0, I get x squared equals 7. And so I get x equals plus or minus root 7. And then, of course, from my x plus 5 term, I got x equals minus 5. So my rational zeros is only x equals negative 5. My other zeros, or irrational, are x equals root 7 and x equals negative root 7. And so if I wanted to factor this polynomial fully, I would have x plus 5, x minus root 7, x plus root 7. And that is the fully factored polynomial and all of its zeros figured out. And it did take some effort with we didn't use long division with the synthetic division. We had to do it multiple times previously in order to find something that was a yes. But luckily, once we broke that off and looked at our factored function, it brought us to something that was a little bit easier to work with. We factored that x squared minus 7, found its zeros, brought it back to its linear terms. So that is it for that example. Let's move on. Here we're going to find only the rational zeros if they exist. So we're going to mind our p's and q's again, looking at p first. P needs to divide this value 6, so that could be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now Q needs to divide the coefficient in front of the x, which here is just a 1, so that's a plus or minus 1, which really we don't have to worry about because we've covered all of the pluses and minuses in the P row. The dividing by another plus or minus 1 doesn't give us any more things to test. So let's cycle through our p's, see which ones are going to be potential zeros. So starting with 1 as a natural first place, let's do our synthetic division. 1, 2, negative 5, negative 4. Oh, and 6. 1, 2, negative 5, negative 4, and 6. Perfect. Now we give ourselves some space, draw a bar, and we drop the 1 to start. 1 times 1 gives me 1. 2 plus 1 is 3. 3 times 1 gives me 3. Negative 5 plus 3 is negative 2. Negative 2 times 1 is negative 2. Negative 4 plus negative 2 is negative 6. Negative 6 times 1 is negative 6. And 6 plus negative 6 is a 0. Look at that. So we got our first 0 right off the bat. That's a yes. And we know 1 is a 0, so we know that our function f of x equals x minus 1 times x cubed plus 3x squared minus 2x minus 6 from these coefficients right in here. Well, that means that we don't have to keep doing synthetic division on the full polynomial. We can start to zoom in a little bit on what we just picked up, this x cubed plus 3x squared minus 2x minus 6 polynomial. So let's see if negative 1 is a root next, and we can now again focus in on the simplified polynomial, the factored one essentially. Like we've pulled out a factor, and so now we can just focus on the rest. Doing synthetic division with this gives us 1, 3, negative 2, negative 6. And so I give myself some space, draw a bar, drop the 1. Now I do 1 times negative 1 gives me negative 1. 3 and negative 1 gives me 2. Negative 1 times 2 is negative 2. Negative 2 plus negative 2 is negative 4. Negative 4 and negative 1 is 4. Negative 6 plus 4 is negative 2. So that's clearly a no. That guy is not 0. Let's see if we can get a different 0. Let's try 3. 1, 3, negative 2, negative 6. Totally reasonable to go through the 2's as well, but I want to jump around a little bit and jump to 3. Draw ourselves a bar. We drop the 1. We do 3 times 1 is 3. We add the 2 of them, we get 6. 6 times 3 is 18. Negative 2 plus 18 is 16. And 3 times 16 is 48. And so negative 6 plus 48 is 42. Well, that's clearly not 0, so that's also a no. Okay, so now let's try negative 3. We do 1, 3, negative 2, negative 6. Draw our bar. Drop the 1. 1 times negative 3 is negative 3. 3 plus negative 3 is 0. Bring up the 0. Negative 2 and 0 is negative 2. Negative 3 and negative 2 makes 6. 6 and 6 gives us 0. So that is also a rational 0. So that tells us now, if you come back up to the top, that we get f of x equals x minus 1 times x plus 3 times x squared minus 2. So now we're most of the way there. If we wanted to pick up the zeros from this term, we'd have to take x squared minus 2, set it equal to 0. We get x equals plus or minus root 2. But these are not rational. And that is not what the question asked for. It only asked for the rational zeros. So the rational zeros are the ones we found, x equals 1 and x equals negative 3. Those are the only rational zeros. We throw out the irrational ones here. But again, it took 4 synthetic divisions in order to get us to the answer. Now let's move on to the Descartes, I believe is how you say his name, Descartes rule of signs. If we have a polynomial p of x that's written in descending order or ascending order, and it is a function with real coefficients and non-zero constant term, then the number of positive real zeros of the polynomial is either the same as the number of variations in sign of p of x or less than the number of variations in sign of p of x by a positive even integer. So essentially we're going to look at the number of times that the signs change from term to term. So do we go from a plus 2 to a minus 5, or a minus to a minus? Where were the actual changes in the signs? And then we take that number and we can reduce it by 2 until we get to 0 or a negative number and we stop. So you're going to see this example of that in a second. We do the same thing when we talk about negative real zeros, except this time we're going to plug in negative x to the function and do the same thing. Look at the number of times that the sign has changed, and then count backwards by 2 until we hit 0 or a negative number. Let's do this in practice. What does Descartes' rule of signs tell us about this number of positive real zeros and the number of negative real zeros? Let's identify our signs first. Here we have a plus, then a minus, and a plus. So here I see a change, and here I see a change. So that means that we have 2 changes in sign. So that means that our positive, the number of positive real zeros is 2, or it could be 0, because we're going to take 2 and we're going to subtract 2 off of it to get 0. Okay, so we got 2 as our number of sign changes. We count down by 2 from 0 till we hit 0. Now let's take that same polynomial here, and we saw the number of positive is 2. Now let's think about the number of, 2 or 0. Let's think about the number of negative. Let's look at p of negative x. If I plug in negative x here, I get negative 2x to the 5. Let me show the details here. Let's plug it in together. 2 negative x to the 5th minus 5 times negative x squared minus 3 times negative x plus 6. Because I want to remind you guys that when we take 2 times negative x to the fifth, when that negative is raised to the fifth, the negative persists, so we get negative 2x to the fifth. It's an odd exponent, so the negative stays. Minus 5x squared. In this next case, the negative gets squared away. That's an even exponent, so it's gone. Now we have a plus 3x and a plus 6. Notice I combine the double negatives on the plus 3x. So now we have a minus, a plus, and a plus, which means we have one sign change. So we can only have one negative 0 for our polynomial. So now I want you to take a look at this chart that we have on the right-hand side, because it helps us determine, well, how many zeros are actually remaining. If my polynomial has degree 5, which remember is the largest exponent written here, and we already saw it can have either 2 or 0 positive real numbers as zeros, and we already saw that the negative real 0 we can only have one negative real 0. So we write down 1 in both of those columns under the 2 and the 0. Then these numbers, this whole column, when I add them together, it needs to equal 5. So I can know then that I must have a 2 down here, because 2 plus 1 plus 2 is what will add to 5 at the top. Essentially, I know I have 2 remaining zeros in this column. Alternatively, on the right-hand side, I know I need these 3 things to add up to 5. And so I must have a 4 as my remaining number of zeros. We call them not real or imaginary or complex numbers, but we aren't covering that in this course. Okay, so we look at the positive number of real zeros, the number of negative real zeros, and then we look at the remaining number. Let's do another example. What does Descartes' rule say about this polynomial? Let's talk about its signs again. We have a plus, a minus, a plus, and a minus. That's quite a few changes. I have one here, here, and here. And so I have, for the number of positive zeros, well, I have 3 because I have 3 sign changes, but I can also have 1 positive 0 because I'm taking 3 and I'm counting down by 2, just as we did before. So I can have 3 or 1. I can't count down by 2 again, or I'd have negative 1, and that doesn't make sense in this context. So I either have 3 positive zeros, or 3 places where my graph crosses the axis, or I have 1 positive 0. Now let's talk about the negative. Let's look at f of negative x. Well, that's negative x to the 4th minus 8 times negative x squared plus 12 times negative x minus 21. And that gives us x to the 4 minus 8x squared minus 12x minus 21. That's a plus, minus, minus, minus. So that's only one change in sign. Well, then the number negative zeros is just 1. Again, we can't count down by 2 here because that would bring us to negative 1, and that doesn't make sense. We can't have negative 1 places where the graph crosses the x-axis. So our number of negative zeros is just 1 here. So bringing this to our table, we said that the number of positive zeros is 3 or 1, and the number of negative zeros is just 1. So let's fill out our chart. The degree is 4, positive is 3 or 1, negative is 1 or 1. Okay, so now I know 3 plus 1 plus the remainder must equal 4. Well, 3 plus 1 already equals 4, which means I must have 0 in my remainder non-real zeros. Now on this side, I have 1 plus 1. That gives me 2. So I needed to add another 2 in order to give me 4 in total. So I know I have 2 non-real remaining zeros. This doesn't tell me what the zeros are, notice. I just know if they're positive or negative on the x-axis, and if there are non-real ones as well, potentially for this function. All right, lastly, we're going to look at one more example of Descartes' rule of signs. Notice, though, that this one technically doesn't satisfy the assumptions in the statement of the rule because we don't have a constant term here. So we actually need to factor out our x term. We get x, and then 6x to the 5 minus 2x minus 5. And that's what's actually going to force our rule to work. We pull out the x, and then look at what happens from there. Now looking at our signs, I have a plus, a minus, and a minus, so I have one change in sign. That means my number of positive values is 1. Now, looking at the negative number of values, I want to focus in on this function in here, which for now I'll call g of x. So to look at the number of negative values, let's look at g of negative x, which is 6 times negative x to the 5th minus 2 times negative x minus 5. Well, that gives me negative 6x to the 5 plus 2x minus 5, which is a minus, a plus, and a minus. That is 2 changes. Therefore, I can have, for my number of negative zeros, I can have 2 or 0. So let's get all of this into a table. So here, remember, we factored out the x. We got 6x to the 5 minus 2x minus 5. And the number of positive zeros was 1. And the number negative zeros was 2 or 0. But because we factored out that x, we know that x equals 0 is also going to be a root. So we have to give that a place on our table. So the degree of this polynomial is 6 because our largest exponent is 6. We know x equals 0 is in there, so we have to have that as a root. If we have a positive number of zeros, we must have it exactly one of them. If we have a negative number of zeros, it could be either 2 or 0. And now just looking at our remaining, I have 1 plus 1 plus 2 gives us 4. I need another 2 of them to give me 6. Then I have 1 plus 1 plus 0. So that gives me 2. I need to add another 4 to get me to 6. So there we filled out our chart for how many positive real zeros, how many negative real zeros, and how many remaining. So that is it for lecture today. Please send me an email if you have any questions. I'm always here to help, so just let me know.